Today we're going to do section 4.1, prime numbers and factoring. The objectives of this section are to prime factorize a natural number, in particular determine if it is prime, find the least common multiple and the greatest common factor of a pair of numbers. In this section we will start exploring the ideas of factoring and prime numbers. We will also look into two applications of factoring, finding the least common multiple, LCM, and the greatest common factor, GCF. The least common multiple will help us as we work with fractions in the next sections, and the greatest common factor will help us down the road to use the distributive property more effectively. Factors. Consider a natural number n. If a pair of natural numbers x and y multiply together to give a result of n, that is, x times y equals n, we call both x and y factors, or divisors of n. We also call n the product of x and y. We often think of rewriting larger numbers into products of smaller numbers and call these smaller numbers factors. Example 1. Identify the factors in the following equations and expressions. 3, 4, and 5 are factors of 60. 15 and 16 are factors of 90. So are 3, 5, and 6. 2, 5, and x are the factors of 10x. As we see above, factors can be either constants or variables, so as long as they are the pieces connected by multiplication. When we are asked to factor a number or expression, we are being asked to rewrite a number as a product of smaller, simpler factors. There are often multiple ways to split a number into factors. Factor the following values in at least two different ways. 24. Well, 24 is 2 times 12. But it is also 3 times 8. You can also find other ways to factor it. 2x squared, well, that can be 2 times x squared. Or it can be 2 times x times x. And then 75, well, that's 3 times 25. Or it could be 5 times 5 times 3. And there are other ways to factor it as well. Recall that natural numbers x and y are factors of n when n equals x times y. Dividing both sides of this statement by either factor gives us another way of defining factors. N divided by x equals y, or n divided by y equals x. Precisely, x is a factor or divisor of n when n divided by x is an integer. In other words, when n divided by x has no remainder. Notice that the result of this division, y, is also a factor of n. Because of this relationship, we call x and y together a factor pair of n. This definition gives us a way of finding factors. If you know what one factor of the number is, you just divide to find out what its factor pair is. Using the idea described above, find all factor pairs of 12. Do you notice a pattern? Well, first of all, 1 and 12. 1 times 12 is a factor pair of 12. And then 2 and 6. 3 and 4. And then these are all the factors of 12, and it can be written like 1, 2, 3, 4, 6, and 12. So on Newton, when it says find all the factors, this is what they're looking for. Prime numbers and prime factorization. A natural number n bigger than 1 is said to be prime if its only factor pair is 1 and itself. Determine if the following numbers are prime by applying the 1 definition. 11 is prime because 11 equals 1 times 11, and that's it. 39 is not prime because it's 3 times 13. So neither of those are 1 or itself, so this is not prime. We also call non-prime numbers composite. 97. This one can be a little tricky. I know 2 doesn't work, 3 doesn't work, 4 doesn't work, 5 doesn't work, 6 doesn't work. Does 7 work? 97 divided by 7. Nope, has a remainder of 6. 8 doesn't work because it's not even, and then 10 doesn't work because it doesn't end in a 0. And because it's less than 100, you only have to check up to 10. If it's bigger than 100, you have to check past 10. So that means 97 can only be rewritten as 1 times 97, so this is prime. We saw above that there are often different ways to factor a single number, since we cannot break them down further like atoms. We are most interested in prime factors, in particular, the process of prime factorization. Involves recursively splitting numbers into factor pairs until you get a prime. We often visualize this process by creating a factor tree. The resulting primes and their counts or exponents are unique. Prime factorize the number below. So like I said, we often do this as a factor tree. So like 8 is 2 times 4. 2 is a prime number, so we're done. 4 is not a prime number, so we break it up again, which is 2 and 2. And then 2 we already said is a prime number. So the prime factorization of 8 is 2 times 2 times 2, or 2 cubed. 18, well, that's 2 and 9. 2 is a prime number, but 9 is 3 and 3. And 3s are prime as well. So we get 18 is 2 times 3 times 3, or 2 times 3 squared. 40 is 4 times 10. Neither 4 or 10 are prime, but 4 is 2 times 2, and 10 is 2 times 5, and those are all prime. So 40 is 2 times 2 times 2 times 5, which is 2 cubed times 5. 95, well, that's 5 times 19. Those are both prime numbers, so the prime factorization of 95 is 5 times 19. Greatest common divisor. Given two natural numbers m and n, their greatest common factor is the largest natural number that is both a factor of m and is denoted GCF. For example, the divisors of 4 are 1, 2, and 4, while the divisors of 8 are 1, 2, 4, and 8. So their common divisors are 1, 2, and 4, because that's what they have in common. But altogether, the GCF of 4 and 8 is 4, is because 4 is the largest there. Example 6, determine the greatest common divisor of each pair of numbers. Well, first we're going to find all the factors, not just the prime factors, all the factors. So we get 1 and 3 for 3. For 12, we've already done that. That's 1, 2, 3, 4, 6, and 12. Well, they have 1 in common and they have 3 in common. So the GCF of 3 and 12 is 3. So that's the brute way of doing it, just finding all the factors and finding which ones they have in common. I'm going to show you the factor tree method now. So what you do is you find the factor tree of both the numbers. And then you find what prime factors they have in common. So they have a 2 in common and they have a 3 in common. So the GCF will be 2 times 3, which is 6. Let's try that for 20 and 30. We see they have a 2 and a 5 in common. So the GCF is 2 times 5, which is 10. Now 75 and 100. I'll go back to the brute method way just so you see it twice. So 75, well, that's 1 and 75. 5 and 15. Oh, I skipped 3. Sorry. 3 and 25. 5 and 15. Then 100. 1 and 100. 2 and 50. 4 and 25. 5 and 20. Now the factors they have in common are 1, 5, 25, and the largest one is 25. So the GCF is 25. And you may see other methods for finding the GCF, but these are the two I'm going to show you today. Now the last topic for this section is least common multiple. Given two natural numbers, m and n, their least common multiple is the smallest natural number, so that m and n are both factors of it, and is denoted LCM. We may instead say that the LCM is the smallest natural number, which is a multiple of both m and n. In practice, we cannot list all multiples of a value since there are infinitely many of them. For example, the multiples of 15 are 15, 30, 45, 60, while the multiples of 10 are 10, 20, 30, 40, 50, 60. So their common multiples are 30, 60, and so on and so forth. Altogether, the LCM of 15 and 10 is 30, because 30 is the smallest common multiple. Notice that any other common multiple is also a multiple of 30. Determine the least common multiples of each of these. So I am going to do it the brute force way first, and then I'll do it with the factor tree method. So the multiples of 3 are 3, 6, 9, 12, 15, and so on. While the multiples of 12 are 12, 24, 36, and so on. And the first number they have in common is 12, so the LCM is 12. Now, the factor tree method for the LCM is a little bit more tricky than the GCF. So first I am just prime factorizing 12 and 18 again. Now here, it's more like Go Fish. So you find the pairs they have in common. So they have a 2 in common. So my LCM will have a 2. They have a 3 in common. So my LCM will have a 3. But then unlike Go Fish, you get all the other factors that they don't have in common. 2 and 3. So then we get 2 times 3 times 2 times 3, which is 36. So let's try that one more time for 20 and 30. So again, 20 can be split up into 2 and 10, then 10 is 2 and 5. 30 can be split up into 3 and 10, and then the 10 is 2 and 5. So what they have in common first, so 2 times 5, then what they don't have in common, which is a second 2 for the 20, then a 3 for the 30. Well, that comes out to be 60. And now let's do the brute force method just so you see it one more time. So multiples of 75 are 75, 150, 225, 300, and then so on. 100, 200, 300, and so on. The number they have in common first is 300, so the LCM is 300. And that's how you find the least common multiple of two numbers. Again, there are other methods besides these two. These are just the two I'm showing you in this video. Final note, the GCF of two numbers times the LCM of two numbers equals the two numbers multiplied for any natural number pair m and n. You can check with each pair in the previous examples, and you'll discover more strategies for finding these in an activity. And that is it for section 4.1.